Hello, everyone, again. Um, and in this week lecture, we're going to cover um, some topics and fundamentals related to modeling the motion of groups of vehicles. If you have watched the last week lecture, um, you may remember that last week we covered how we can model the motion of a single vehicle. In today's lecture, we're going to talk about how we can actually model the movement of a group of vehicles that they move together. This is closer to what we really think about traffic, right? So as I said previously, we only model the movement of a single vehicle, assuming the vehicle has no interaction with adjacent vehicles. And in fact, it is the interaction between vehicles that create what we see in traffic, that create the traffic operational conditions like capacity, congestion, the operational speed of traffic. So without the interaction between cars, if it is a single vehicle alone driving on a road, there's no traffic. But as soon as we have multiple cars sharing the road, we'll start seeing some traffic phenomena happening, whether it's speed drops or capacity drops that we'll talk about later in this course. And usually, when it comes to modeling vehicle interactions, we model three different type of interactions. The first one is called car following. The second one is called lane changing, and the third one is called gap acceptance, which is related to lane changing. So speaking of car following is the process by which a vehicle follows another vehicle in traffic in close proximity. Car following occurs when the speed of the lead vehicle actually affects the speed of the following vehicle. So if two vehicles are close together, that they can interact really, we have a lead vehicle, we have a follower vehicle, and the follower vehicle, the speed of the follower vehicle, the acceleration of the follower vehicle, whether the driver pushes brake or not, depends on how the lead vehicle behaves. So if they're getting very close together, the follower vehicle may slow down. If the lead vehicle is accelerating, the follower vehicle may also start accelerating. So there is a very interesting interaction happening between the lead vehicle and the follower vehicle. Car following algorithms provide the trajectory of the following vehicle as a function of the lead vehicle, as I just described. So when we're talking about car following models and car following algorithms, what we really do is we really try to predict where would be the location of the follower vehicle, what would be the speed of the follower vehicle, what would be the acceleration of the follower vehicle as a function of what the lead vehicle does. If it's accelerating or decelerating or stopping or going. And obviously, the closer the vehicles follow each other in traffic, the higher the capacity will go. So if we have cars following each other with a very large buffer, with a very large distance from each other, that means the road is carrying less number of vehicles per hour. But if vehicles are very close together, the capacity goes up. And the behavior of the vehicles following each other affects the speed of the facility, as you can probably tell, and that's where I think where we can relate to how autonomous vehicles or self-driving cars, as you might have heard, can improve traffic. The improvement that comes from autonomous vehicles affecting traffic flow is mainly related to the improved capacity at the facility, because autonomous vehicles can supposedly move closer to each other compared to humans, because humans have reaction times, maybe a second reaction time or 1.5 seconds reaction time when it comes to reacting, when it comes to pushing the brake or accelerating, decelerating. But because autonomous vehicles or self-driving cars are expected to be smart and run by computers, so that the reaction time doesn't really exist, or it's very, very small. And so that means two vehicles can actually follow each other, two autonomous vehicles can follow each other with a very, very small distance. And that is expected to increase. That is usually seen as something that we can improve the capacity of the road with. But anyways, I just wanted to make an example that how self-driving cars might affect road traffic as opposed to human-driven vehicles. In terms of lane changing is actually defined as the process by which a vehicle decides to change lane. And it generally involves three steps. One is the driver has to decide to change lane. So when we're talking about lane changing, the first step is the driver's decision on lane changing. Should I change lane or just should I stay in my lane? The second step is selecting the target lane. Okay, now if I decide to change lane, which lane should I change to? Should I move from lane 1 to lane 2? Or should I move from lane 1 to lane 3, going over lane 2? So which lane do you want to go to? That's another decision. That's another selection that the driver has to process. And the last step is selecting the suitable gap. So you don't change lane as soon as you make a decision to change lane. You look for a gap, right? For those of you who have driven or who drive on a daily or regular basis, or you've been a passenger in a car, you've seen that how driver reacts. When you want to change lane, you look in the mirrors, you try to find a suitable gap, a gap that is large enough so you can safely change lane, right? So that selection of a suitable gap can also be modeled, interestingly, with mathematics. And as I said, lane changing is directly related to gap acceptance. So speaking of gap acceptance, as I said, the gap acceptance involves the selection of a suitable gap. We usually define suitable gap as the time headway between the rear end of the lead vehicle and the front end of the following vehicle. And or to cross a conflicting stream. So for example, if there's an intersection, you want to cross the traffic stream. For example, if there's a stop controlled approach or if there's a give-way approach, you look for a large enough or a safe gap to be able to cross. But why do we need all these gap acceptance models, or why do we need these lane changing models? All these models can actually be implemented in traffic microsimulation. So I'm not sure how many of you are familiar with traffic microsimulation, but let me show you some simple videos that we might find on YouTube when you search for traffic microsimulation. There are multiple simulation softwares that are usually and widely used in industry. AIMSUN, Vissim, what else? We have Paramix, we have Sumo is an open source free one, it's not commercial. So there are many options out there when it comes to commercial softwares that traffic engineers can use to model or simulate traffic. And behind the micro simulations that you'll see in a second, there will be all these mathematical models that we're going to cover. That is implemented and is visualized like a traffic microsimulation. So let me show you an example video of microsimulation. In this video, it's a demonstration of using AIMSUN microscopic simulation to model two-way overtaking. So let's have a look. So we'll start with usually looking at the satellite images and selecting the stretch of the road that we would like to model. And you can see then we draw the lines, the streets, the road sections. We draw the intersections in the software. We put the number of lanes. We input the free flow speed, the capacities, the signal timing, the location of public transport stops, for example. And then if I move a little bit forward, that's how it works. Yes, that's how the software actually looks like. So look, you start drawing the two-lane road, for example, and then I mean we're gonna cover some of these AIMSUN simulation in later weeks, but just want to show you how a traffic. So yeah, there you go. So after, for example, you build the network, you build the road sections that you want to model, you want to simulate. Then if you run the simulation, this is what you end up seeing, that you'll see cars moving around. And as I said, behind this nice visualization, there are a lot of mathematical car following and lane changing and overtaking models. I mean, we're not going to cover how the overtaking modeling, but that's another kind of traffic behavior that can be modeled. But here you can easily see the car following behavior when two vehicles are moving close together. And overtaking is kind of it's also another gap acceptance. It's also related to gap acceptance, right? So you overtake another vehicle when you see there is enough gap between your location and the location of the car coming in front of you in the opposite direction. So this is how usually a micro simulation looks like. And now let's dive into the actual topics that we would like to cover and we would like to model and learn about this week. So the first one, as I said, is car following. Let's consider two vehicles, one traveling behind the other in a single highway lane. So there's only one lane and there's only one direction. And so we're going to go with a very simple case. There's one lane and there's one vehicle leading and there's another vehicle following. So the movement of the first vehicle on the road, which we call lead or leader, is primarily defined by the motion principles and the equations of motion we discussed before. So if you are the lead vehicle and there's no vehicle in front of you in close proximity, so your driving is not affected by traffic, right? You're the first vehicle on the road and you just drive based on the motion principles that we talked before, the way you accelerate or decelerate, or what speed you choose, and where your location will be in some time in future. So all of that will be following the equations of motion based on kinematic physics. However, the movement and trajectory of the second vehicle, the third vehicle, or the fourth vehicle, so all the vehicles in the platoon, which can be considered as the follower of the lead vehicle, are based on additional factors that we must take care to avoid a crash between the two vehicles. So most of the car following models, what they do is one of the main factors that they take into account is we would like to prevent the follower crashing into the lead vehicle, right? And because that's how it usually works in reality. If you are the follower, you try to keep a safe distance. At the same time, you try to maybe go with the speed that is possible, of course, equal or smaller than the speed limit. But at the same time, you don't want to crash into the lead vehicle. So that crash avoidance, that safety distance that I just touched on, is a very important factor in car following models. So imagine, let's first have a look at one case, the case one. So imagine the lead vehicle is traveling free from traffic ahead, and its speed corresponds to the driver's desired speed. The following vehicle's desired speed is lower than the lead vehicle. So what I'm saying here is the lead vehicle is traveling free of traffic with whatever speed the driver wants to, and the follower vehicle has a speed lower than the lead vehicle. What will happen? The question is, will the follower be constrained by the position and the speed of the lead vehicle? Is it yes or no? Obviously, it's no, because if the lead vehicle is going fast and the follower vehicle is going slow, the follower vehicle is not getting closer to the lead vehicle. So as time goes ahead, as time moves, the distance between the leader and the follower increases, right? So the spacing between the two vehicles keep increasing. As a result, the behavior of the follower vehicle is not constrained or limited by the position, speed, or acceleration of the lead vehicle. However, in case two, imagine the lead vehicle, again, is traveling with free flow speed, with whatever desired speed the driver wants. And here, the follower desired speed is actually higher than the lead vehicle. So what will happen is I have a leader, I have a follower, the follower is going faster than the leader. What will happen is over time, the follower gets closer to the lead vehicle. And that's where at some point, when they get close enough, the follower vehicle, we call it, enters a car following state, where the spacing, the speed and acceleration of the follower will be dictated by the lead vehicle. Now let's have a look at this case in a time-space diagram and have a look at a trajectory example as we learned from last lecture. So imagine this time-space diagram and we have two trajectories. This is trajectory A or vehicle A, so this is the lead vehicle. And this one is the follower vehicle. So this is a follower. And you can see that this is mainly representing case 2 because if you look, the lead vehicle is going with the constant speed. The slope of this line is fixed almost, right? So that means the lead is going with a constant speed. However, the follower vehicle before T1, it's actually going with a higher speed. You see the slope of this trajectory is higher than the slope of this trajectory. So that means before T1, the follower was actually going with a higher speed compared to the lead vehicle. But at some point, when the follower gets closer to the lead vehicle, the follower has to slow down, right? Otherwise, it would crash to the lead vehicle. So we can see here that the follower slows down. So there is a little bit of deceleration here happening, and then it follows the lead vehicle with almost the same speed. So if you compare the slope of this trajectory and the slope of this trajectory, the slopes look similar, right? So this would be VA and VB. The slope of the trajectory, which represent the speed, seems that they're almost the same because the location of vehicle B, the location of the follower, the speed of the follower is constrained by how the lead vehicle is behaving. So imagine now, if I erase these, and imagine now the lead accelerates and speed up. So imagine vehicle A starts accelerating and speeding up. What will happen? Vehicle B will soon see enough space in front of it, and then vehicle B also start accelerating and going faster, right? As long as it's legal to speed up, right? As long as they're all moving with the speed that is lower than the speed limit. And some interesting measurements that we can do on this diagram, if I can erase some of these lines that I drew to make it a little bit cleaner to work with. Look, the horizontal distance between these two trajectories, what does it represent? The horizontal distance between two trajectories in a time-space diagram represents time, right? Because it's on the x-axis, it represents time. So this t here, this delta t here, it's called time headway or headway. Headway is the time between the two vehicles. However, the vertical distance between the two trajectories on a time-space diagram, so again, the vertical distance between these two vehicles, so this is going to be delta x or delta L, whatever we call it. This one represents the spacing or the distance between the two vehicles. So here I'm introducing two very key measurements in traffic that is called headway and spacing. Spacing is in the unit of distance, while headway is in the unit of time. And working with a time-space diagram and trajectories, the vertical distance between two trajectories in a time-space diagram represents a spacing, and the horizontal line between the two trajectories represents headways. Now imagine we have multiple groups of vehicles that are following each other. So we have group X and group Y, and each group has a lead vehicle, right? This is lead, and all the others are followers. And in the other platoon, so these groups can also called also platoons. platoon, if you haven't heard that word before. Platoon means a group of vehicles following each other. In group Y, this is going to be the leader vehicle, and the rest of the vehicles are followers. So now let's start modeling this. Let's put some math into all these concepts. So in a car following algorithm, we determine the movement of the following vehicle at time t plus delta t, so at some time in future from time, as a function of its relationship to the lead vehicle at time t. So imagine this is time t. I have the lead vehicle, and this is the follower. For example, let's call lead vehicle n. Let's call the follower vehicle n plus 1. And the time between the two vehicles is called headway. And the distance between the two vehicles is called the spacing. So this is headway, and this one is called spacing. Now imagine some delta t passes, and we are at time t plus delta t. So vehicle n moves a little bit, you see. So vehicle n, if I look at the front bumper of the vehicle, I can see that the vehicle has moved like this much. And the follower is also moved. So this is the front bumper. This is the front bumper. I can also see that this vehicle is also has moved this much. So the distance that is traveled by the lead can be represented by dn t plus delta t, right? The distance that vehicle n has traveled from time t to time t plus delta t. And this one is the distance traveled by vehicle n plus 1, which is the follower, from time t to time t plus delta t. And as a result, we have a new headway and new spacing, right? So that can be represented as ht plus delta t, ht plus delta t. That's the headway. And there's also a new spacing. It's st plus delta t. So these are the kind of notations that we're going to use in car following models. So I think this is basically what I talked about, so I don't want to repeat myself. You can have a look at this later if you like to read what I just talked about. But let's dive into the first car following model. The first one that I would like to introduce you today is called Pipes model. The Pipes model is actually a very old model. It was introduced by a scientist called Pipes in 1953 in a paper that he published in Journal of Applied Physics. Look, a very interesting journal. It's a physics journal because, as we talked about, many of these car following and vehicle motion falls in the general kinematic physics, right? And there are many physicists that are interested in how to mathematically model movement of cars, because it's very similar to how, for example, gas moves in a pipe, or how a fluid moves in a pipe, right? So same concept, same way of thinking can be applied when it comes to modeling traffic on a road. It's like water moving in a pipe, right? But anyways, so the Pipes model has a main assumption, and the assumption is that the distance of the follower vehicle to the lead vehicle is equal to one vehicle length. So Ln represents the length of a vehicle for every 10 miles per hour. So if you are going 10 miles per hour, you keep a distance of L between the two vehicles. If you're going 20 miles per hour, you keep a distance of 2 vehicles. If you're going 30 miles per hour, you keep 3 vehicles distance from the lead vehicle, plus a minimum distance between the vehicles at a standstill. So if the 2 vehicles are totally stopped, let's say in congestion, they don't necessarily touch each other from in the front bumper to the rear bumper, right? If you're still stopped, you still have some minimum distance between the two vehicles when they are at standstill, and that is usually represented as b. So the way we can mathematically write that as a rule to satisfy this assumption is that we say, what I can write is this one, that xn minus xn plus 1 that is the distance between the two vehicles, right? So if I have the lead vehicle here and I have the follower vehicle, so this is the lead and this is the follower. And again, if I look at the center point of this, or if I look at the front bumper to the rear bumper, maybe, this distance is xn minus xn plus 1, right? So the distance between the two vehicles is actually equal to the standstill minimum safety plus the length of a vehicle plus something called S-min, which is the minimum distance between moving vehicles, which can be estimated as t multiplied by the speed of the follower. Remember, the lead was n, the follower is the vehicle n plus 1. So Vn plus 1 is the speed of the follower, where t is the time that it takes to travel the minimum distance in seconds, and v is actually the speed of vehicle. And in this case, it's Vn plus 1, and that is the speed of the follower vehicle. This formula is actually representing this assumption that I talked about that says for every 10 miles per hour, we want to keep one ln plus that minimum distance at a standstill. So let's have a look at an example here, so it becomes a little bit more clear how Pipe's model works. So as a rule of thumb, we can say that a good rule for following another vehicle, following the Pipe's model, is the following another vehicle at a safe distance is to allow yourself a length of a car about 15 feet for every 10 miles per hour. So this 15 feet is actually ln, right? Which is the length of a vehicle. And if we convert it to the metrics that we're more comfortable to work with, 15 feet is almost equal to 4.5 meter. And that 10 mile per hour is also about 16 kilometer per hour. Okay, so Pipe's model says for every 16 kilometer per hour of a speed, you need to keep a distance of 4.5 meter. So now let's have a look at a simple question. If a vehicle is traveling at a speed of 80 kilometer per hour, what is a safe distance to the vehicle in front? So in this case, it would be the speed is 80 kilometer per hour. So we want to know how many of 60. So we do 80 divided by 60 and multiply by 4.5, because for every 16 kilometer per hour, there should be a safety distance of 4.5 meter. So now that we're going with 80 kilometer per hour, we want to see how much distance should we keep, and that would be simply 80 divided by 60 multiplied by 4.5 meter, which gives me a safety distance of 22.5. Okay, so that would be S-min, right? And if I want to relate this to this formula that we had in the previous slide, that we said S-min can be represented as T multiply Vn. So let me write it here. So it would be S-min is actually T multiply Vn plus 1. In this case, what is the speed of the follower? The speed of the follower is 80. And T, how did we define T? T was the time that it takes to travel the minimum distance. So that is basically 4.5 meter divided by 16 kilometer per hour. That represents the time that it takes to moves one length of a vehicle, right? So this is T multiply Vn. So this is V, and this is actually T. And then this gives us 22.5 meters. So that would be S-min. That would be that safety distance that we're talking about. And now if you want to put it in the time, so we have S-min, we have the length of a vehicle. We can assume a B of, I don't know, 2 meter, 3 meter for a minimum distance between vehicles at a standstill. And then that would give us xn minus xn plus 1, the distance between the two vehicles. Now let's do some interesting and very easy mathematical operations here. Now imagine we replace S-min in the Pipe's model with T Vn plus 1. So this was S-min, and we're now replacing it with T multiplied by V. If we differentiate this formula, what do we get? When you differentiate X, you get the speed, right? So dx over dt can also be represented as x dot, and that is the speed, right? If I again differentiate this one more time, that would be acceleration, or I can put two dots on x, and that's acceleration, right? So now if I differentiate it once, I get the speed of the lead vehicle equal to the speed of the follower vehicle. And because all of this b and ln are fixed value, constant values, um, we can cross them out because we're differentiating. And what we'll end up with, we keep the t, and then we have to differentiate this v. And differentiation of the v, the first derivative of the v represents acceleration, right? So this becomes v dot and an, which is basically a n plus 1. That's the acceleration of the follower vehicle. Now, if I rewrite this into an easier formula to work with, that is the speed of the leader is equal to the speed of the follower plus t multiplied by the acceleration of the follower. And if I keep acceleration in one side of the equation and move everything else to the other side of the equation, what do I get? So Pipe's model says the acceleration of the follower is equal to the speed of the leader minus the speed of the follower divided by that t, the t that we talked about, the time that it takes to move the distance, 1 ln. And that's how Pipe's model work. So we have an equation for x, we have an equation for v, and we also have an equation for acceleration. And when we have all these equations of motions, we can actually start modeling car following. I have a little maybe practice problem for you that you can work on yourself at home or elsewhere. It's in MATLAB. It's just it's not mandatory for you to work on this, but it's totally optional. What I would like you to challenge yourself with is, can you code Pipe's car following model in MATLAB? So try to model a ring road with the periphery of 1 kilometer, and try to have one vehicle, try to have 10 vehicles, model 10 vehicles on the ring. So these are all vehicles, so they're not 10, but you model 10 vehicles here. And each of them is keeping a distance of 4.5 meters on the ring. And then you randomly assign an initial desired speed to each vehicle. So for example, this vehicle can have a 40 kilometer per hour desired speed. This vehicle can have 50. This vehicle can have 55. This one could be 45. This one would be 60, 57. So you assign a random desired speed from 40 to 60 to each vehicle. And then you start moving them using the Pipe's car following model. You can assume a minimum standard still of 2 meters, and you can assume t is 1.023 seconds. That t is being used in that S-mean calculation as we talked about. And then what I would like you to do to challenge yourself with is, can you code this in MATLAB and analyze the impact of increasing or decreasing the density and congestion? So for example, if you increase the number of vehicles, what will happen? If you decrease the number of vehicles on the ring, what will happen? How the car following model behaves. This might be challenging for some of you who haven't had much coding experience, but again, give yourself give it a try and see how you do, if you like. So the next car following model that I would like to introduce here is called a stimulus response. A stimulus response is a general branch of car following models. So for example, GHR model or GM model, they're all kind of a stimulus response type car following models. Pipe's model is similar to a stimulus response model. There are also some models developed. There's also the model that's called GHR, is originally proposed by Gazis, Herman, and Rothery many years ago. And another model that is called GM is actually developed by General Motors, the manufacturing company, the car manufacturing company. And the way stimulus response models work is that they consider the sensitivity of the reaction to the lead vehicle. Because, again, as a driver, you might be very sensitive to how the lead vehicle drives, or you might be less sensitive. So, for example, if the lead vehicle accelerates, would you accelerate as much? Or you don't necessarily accelerate as much as the lead vehicle. You'd prefer to go, maybe with a smoother movement. So the general formulation of a stimulus response type car following models is like this, where on the left side, I have the acceleration of the follower at time t plus delta t. And again, look at the right side of the equation. Let me first start with this. I have the difference between the speed of the leader. So this is the leader speed, right? So this is the leader speed. This is the follower speed. And you can see there it's at time t. It's not at time t plus delta t. It's all at time t. And then in the denominator, what do I have? I have the distance between the follower and the leader. So this represents the distance between leader and follower. There is a power here, power L. This L is a parameter to be defined or calibrated, okay? We also have the speed of the follower here at time t. So this is the follower speed. Again, that also has a power m, which needs to be calibrated and assumed. And we also have another parameter called lambda. This lambda is also a sensitivity parameter that needs to be calibrated, and if you have some data. So this is how stimulus response models work. Again, if I go back to the pipes model, look at the acceleration formulation in the pipes model. The acceleration of the follower in the pipes model only depends on the difference between the speed of the follower and the leader. However, in the stimulus response models, not only we have the difference between the speed of the follower and leader as here, but what matters is also the distance between them and also the actual speed of the follower. So it's a more sophisticated and maybe more complete way of modeling car following model compared to pipes model. And again, what is interesting here is stimulus response models try to incorporate time into the equation, which the acceleration of the following vehicle at time t plus delta t is a function of the vehicle's status at time t. So if I go back, look, what I'm modeling here is I'm trying to model the acceleration of the follower vehicle at time t plus delta t as a result of all these notations that I talked about, the difference between the speed, the difference between the locations, the actual speed of the follower, all at time t. So whatever is happening at time t, I'm going to use that to predict the acceleration of the follower at time t plus delta t. Now let's dive into this, and let's assume m is equal to L is equal to 0, right? So if I go back to the original formula, what will happen here if L is equal to 0 and m is equal to 0? So this would be 0, this would be 0. So the denominator would be 1, this v power 0 would be 1. So what I end up is a simple formula that lambda multiply Vn minus Vn plus 1, right? So if m and L is equal to 1, that stimulus response general formula reduces to this simple equation, which acceleration of the follower is equal to lambda multiplied by the difference between the speed of the follower and the leader. And that is called the GHR model, right? This was the first form of the GHR model, which was tested and calibrated many years ago in 1990, actually. Maybe actually even earlier. This is a book. This is a reference to a book. I mean, I can try to find the actual paper, but I don't have it here. And lambda, based on some actual data, is calibrated to be between 0.17 and 0.74. So you can see the stimulus response general formula is reduced to this simple formula that acceleration of the follower is only dependent on the difference between the speed. This isn't very different from the pipes model, right? There's only this lambda variable here that tries to correct, that differentiates this simple GHR model, the very first form of the GHR model compared to the pipes model. So what are the shortcomings of this GHR model? So when the vehicles travel at the same speed, when the speed difference is 0, the GHR model cannot really estimate the reaction of the following vehicle, because if the vehicles are going with the same speed, right, this would be 0, so the acceleration would be 0. So there's no indication of the distance, right? So we don't know, regardless of how far these two vehicles are, if they are very close or if they are far, if they're going with the same speed, Pipes model says acceleration is equal to 0. Acceleration of the follower is actually equal to 0, which may not necessarily be true. The speed difference determines whether the following vehicle will accelerate or decelerate, regardless of the vehicle's spacing. Because that m and l is equal to 0, there's no spacing involved in the calculation of acceleration here. Also, when the following vehicle's speed increases, the sensitivity of the following vehicle also increases. Thus, at high speeds, the model becomes too sensitive to the stimuli from the lead vehicle. So in this case, look, if the speed of the lead vehicle is high, the acceleration keeps increasing, right? So if this vehicle is going with 40 kilometer and this vehicle is going with 50 kilometer versus if it goes with 60 kilometer, the difference here is 10, while the difference of the speed here is 20. So it actually doubles, the acceleration doubles just because the lead vehicle is going like 10 kilometer per hour faster. So it becomes too sensitive when the lead vehicle is actually going with a higher speed. So another practice problem for you if you want to challenge yourself, and that is very similar to the implementation of the pipes model. If you would like to challenge yourself, go ahead and try to code GHR model in MATLAB in the same settings. Imagine we have a ring, place 10 vehicles on the ring, and try to model GHR model assuming lambda is 0.25 and the L and M are equal to 0, and then try to analyze how increasing or decreasing the number of vehicles on the ring affects congestion. And then you can compare your simulation results with the pipes model as well. But again, this is totally optional. If you're comfortable with MATLAB and coding, you can give this a try.